Okay, so just before we get going, Gary's going to continue with the GC today, and I'll continue general chromatography on Wednesday. But very quick note regarding the quiz. Since probably you saw my email, since several of you had issues with timing and also uploading. So we are opening it for 15 extra minutes. So you can go in and complete questions you have not been able to complete or answer questions that you have not started yet. So do not rewrite everything. Do not re-answer everything. You only have 15 minutes to address those questions that you felt that you were rushed. So you didn't have a complete answer or you didn't even get to. So we have that. And then I think Laura opened it till 9 p.m. today. So you can go back and take those extra minutes to finish whatever question you needed to work on. So we will combine your answers with the previous quiz answers to get you your final grade. Okay. All yours, Gary.
Okay. You said the mouse comes off the side. I'll try to have the mouse.
So where's my mouse now? It's right here. So it's here. And then if you go to the left, it brings you back here. And then if you go here to the right of this, it brings you back.
You can go right around the block.
Yeah, so you're here.
Okay. Good. So let's see. We'll park it right there. Okay. Anyway, so we started talking about gas chromatography last time and getting into kind of the options for injection port. You know, how do we inject a sample? How does that work? We're into, well, at this point, actually, of course, the detectors. And, you know, I'm going to say some things about detectors and say things about problems and so on. And there's a reason for it. If you're in an analytical laboratory, you should know how the equipment works. You should know every part of that equipment. They're not a box where you put something in and get a number out. The better you understand that instrument, how it works, how it needs to be maintained, the better data you're going to get. And the happier people will be with your data. So, you know, don't take it lightly when we go through something like this in terms of detail. It really is important. So I mentioned first, in terms of detectors, I talked about the thermal conductivity detector. That was the first detector that was really put on a gas chromatograph, and it's still around. It's still around for some very good reasons. And one of its main reasons is, well, let's do two of them. The first one is it's non-destructive. All these other detectors are going to make my sample disappear. And if that's a problem, if you want to collect something comes off, oh, that peak, I'm interested in it. Let me get some of that and do mass spectrometry or NMR or something. Well, anything but thermal conductivity, you don't have a sample left. So that's really an advantage. Another thing is the universal detector. It will detect anything. Not great in terms of sensitivity, but it is a detector that will detect any material. All of the other detectors I'm going to talk about are fairly specific. And so this is our next one. This is the workhorse. I would guess probably 90% of gas chromatography is done using a flame ionization detector. And the way this works is we'll get the sample coming in, if I can go the right direction here. We get the sample, it does work kind of like you're doing. Comes in from your column. Well, we may or may not end up doing this. Okay, so it comes in at the bottom. I'll do it that way. I'll point and everybody at home can say, where do you point? Anyway, so we've got the column coming in the bottom right-hand side. As your column effluent, whatever's coming off that column, goes straight up that tube on the right-hand side. You'll see H2 inlet and makeup, then a tube coming in on the side or line coming in the side. That's hydrogen, that's flammable gas. So I'm putting a little bit of extra gas in there and I'm putting a flammable gas in there because then we're going to mix these two together. There's an air inlet up on the top left And so what do we have? We got hydrogen, we have air, and we have our column effluent. It's going to create a fire. There's going to be a flame, and you see the flame right where it says capillary position, capillary column, and position. There is a flame. And as things burn, they form ions. And so what we have is that bottom of the flame is grounded, an electrical ground. The tube right above that flame carries 300 volts of electricity. And so what the machine is going to do is, as things burn, that flame is going to carry electrical current. The more material that it's burning, the more ions. The more ions, more current. So we get electrical current that's proportional to the amount of compound being burned in that flame, compound coming off the column. And so it's really a very good column in that, or a good detector in that sense. It really responds well to organic compounds. Doesn't do a darn with anything metallic, doesn't do anything with water, doesn't do anything with other gases, but it's great for carbon-containing materials. So organic materials, that's us. That's what we do. We do food, organics. And so it is specific in that sense. It has to be an organic compound. Sensitivity, I must have at least 10 to the minus 12th grams of material coming into that flame to get a measurable response. 10 to the minus 12th, and this kind of start putting a period and then 0, 0, 0, 0 to get out to 12. That's not too bad. You know, that you don't carry that around in a bucket. It's a fairly sensitive detector. Linear range also. If we got compounds that differ by 10 to the 6th or 10 to the 7th in amount, it still will give you a proportional response. And so when you're measuring things and you've got several different materials in your column, including in your analysis, you may want to know how much of each. That's nice if it's a linear response. You can do that calculation very easily. There are some adaptations of this called the alkaline flame detector that does make it specific for nitrogen. So I can measure only nitrogen containing compounds. So either all organics or specifically nitrogen containing materials. This is an electron capture detector. So we've got, again, the column coming in the bottom. It enters into that chamber, and you see there's a little rod pointing down. So that rod, again, is an electrical connection. The interesting thing is that the inside of that channel, inside of that opening, is actually coated with a radioactive substance. It gives up, as a part of its degradation, electrons. So there's always electrons flowing from the radioactive nickel into that center rod. So we have always a current. Now, as any compound comes in there and flows through that column, what'll happen is if those compounds absorb electricity, electrons, it's going to reduce the electrical flow. So this one always has an electrical flow, and anything that goes through there that absorbs electrons, it measures it. So very, very simple technique. It is very selective, sensitive, especially to halogens. Where do we find halogens? Very commonly in pesticides, herbicides, a number of not food additives, but packaging materials and so on. So we got a detector here that really does quite well, looking at some things that we're specifically interested in. No response with ordinary organic compounds, no response to water, to gases, whatever. But like I say, particularly halogens, conjugated carbonyls, nitriles. So very specific. Sensitivity, 10 to the minus 14th grams. Okay, we're doing quite well at this point. Linear range, well, only a factor of 10,000. If things, you've got two components in there, they differ by more than 10 to the 4th, you can't say they're linear. So they're kind of pseudo-linear beyond the 10 to the 4th. The radioactive detectors do have a limited temperature, but that's really not a problem in normal. It's really a good detector, particularly, like I say, pesticides, herbicides. Chemiluminescence, my bag is flavor. I study the flavor of foods. And in the flavor of foods, sulfur compounds oftentimes play a very important role. So I'm interested specifically saying, okay, what things and what I smell, what I eat contain sulfur. This is one of two detectors that is able to detect specifically sulfur-containing analytes. We've got a reagent gas coming into the reaction chamber. We have our column effluent coming into that chamber. The reagent gas mixes with what comes off our column, and we get a chemical reaction, a luminescence, a giving off of a particular wavelength of energy that simply gets monitored by a photometric device, and that's our detector. No sulfur, no response. Flame photometric is somewhat similar, does the same thing, but in that case, I've got like a typical flame ionization detector over on my left, and my column effluent is burned in the flame. I'm sure all of you, in either atomic emission spectroscopy or at the Science Museum, if you've ever gone down and looked at burning different elements in a flame, if you burn different elements, they give off different light waves, different spectra. And so here we've got a flame, we've got a filter that only lets sulfur-containing emissions come through. So again, really nice specific detector for sulfur components. There are other choices. There's several different choices, but we did have for a while Fourier transform infrared detector. That's really gone away. What we have now that takes the place of some of our detectors is mass spectrometry. So we're going to put at the end of a gas chromatograph a mass spectrometer. So there's no detector except the mass spectrometer. Okay. That gives a fingerprint and or a molecular weight of what just eluted from the column. It's an extremely desirable detector, and I'll give you some examples of why it is so good. The idea of what do we use MS for? You're going to get 2 lectures on mass spectrometry, so we won't go into how it works at this point. But the idea of knowing what compounds just came off your gas chromatograph. You isolated something from foods. You isolated a lot of things, perhaps, from foods. Well, what are they? You've got a peak here, peak here. How do you know what they are? Well, that's where a mass spectrometer really comes in handy. Whatever elutes from your column goes into the MS, and the mass spectrometer gives you, hopefully, an identification. Not always, but hopefully an identification. The idea that there's another benefit to it that I really like, and that's that I can quantify compound without analytical separation. And so I may have some peak, some compound eluting from my gas chromatograph, giving me this nice peak. That may be 2 components and maybe 3 components, but they still form a nice peak. Okay, my MS can start taking those things apart and say, no, that's not 1 compound, that's 2. And this is what this one is, and that's what this one is. So it's extremely powerful as far as the detector goes. This is an example of that power. Down in your lower left-hand side, you've got a little orange chromatogram is what we'll call it. It's the output of the detector. So we're finding, okay, here comes this component. Each peak is a different component. And we've taken just a little section out of that total run and made it larger right above. So you've got your orange, which is what's being drawn that we see down below. But then we've got under that, we have other peaks. And it's interesting that those other peaks are other compounds. So we might, without knowing, we might say, oh, that one peak, that's 1 compound. The second peak's the second one. Third's another one, but it's more than that. There can be 1, 2, 3 peaks underneath one of these. And we misreport it. We give the wrong data. We give the wrong numbers if we don't know there's really 3 things we're measuring instead of 1. And so just that last peak, we got 3 of them on your upper left. On the lower right, we got that 3rd peak expanded so you can see it a little better. Left off, there is another component, a green one in there that isn't showing up, or we didn't show up. And so what we do is we go ahead and take a look at the spectrum that's coming off, and we can actually, like I say, see there's 3 different peaks. how do we, well, now I'm again expanding it a little bit more. What you find is that two of those peaks, there's a green peak and a purple peak up there. And so we can notice there's a slight difference in time. There's less than a second difference. There's a half a second difference between the peak of the green peak and the purple peak. So that the spectrometer is taking this whole mix of ions that gets out of the machine and says, hey, this set is going along at exactly this time. Oh, this other set's going along at a different time. These must be two different compounds. And so then it says, let's look at each of these sets that are moving together and let's see if we can identify them, what they are. And that's what's shown over on the bottom of this. The peak 37, the top one where it says caliper, that's the combined spectrum. That's the mess that you get out. And I say it's a mess because if you put that into a machine and into a computer, it wouldn't know what to do with it. That's not a real compound. That's the sum of the two that make up that one peak. But if we look down below at the left middle, that's one of those compounds. And then what the computer does for the mass spectrometer goes through a library and says, do I have another fragment like that someplace? Oh, down on the bottom left, that's cyclohexane, 1-ethyl, 2,4-dimethyl, perfect fit. So it made a perfect fit to one set of ions moving through. It does the same thing on the other one. In that case, it's the purple ones, the purple ions. And we've got another unique spectrum there, do a library search, and we find out it's a different compound. So it's interesting. We don't separate those two compounds, but we can separate them now by looking at ions. We can measure the height of those ions, and we can actually do quantification of compounds without complete separation. That's tremendous power. In my business, working with flavor, volatile compounds, aroma, there are 11,400 chemicals that have been identified as odorants. It isn't often we get just one or two. We end up with a mess, with a mixture. So the idea of resolving mixtures to me is extremely important. It may not be as important in some other applications, but if you have a difficult separation, this is really a fantastic tool to work with. So those are our detectors. Now what we're going to deal with is the idea, how do we make a chromatogram, or chromatograph, I should say, do better? Our whole purpose is to separate and measure, quantify compounds. And so our RS over there refers to our resolution. How good are we resolving peaks, separating those peaks? We've got three different factors. Selectivity. Selectivity relates to the column that I just put in. So we have many different types of columns that can go on our instrument, many different coatings. Well, if we pick the right coating that has an affinity for what we want to measure, we can really help in separation. If we've got the wrong column in there, we don't get separation at all. So let's think about a selectivity. Let's get the right coating inside of that column to get the interaction we want, and resolution we want, or separation of components we want. Capacity is a little different term that isn't too important to us here, but that's more or less the idea of where things elute, how fast they elute. If something is coming out right with the solvent very early, it's hard to separate them. We're not getting much interaction. You know, the carrier gas is going through, compounds are going through without any interaction. You don't get separation, so capacity. And then we got theoretical plates. Now, I'm not quite sure how this happened or what, how we came up with these numbers, but we talk about theoretical plates. Do you explain? Oh, good. Then I don't have to. We'll skip it. Okay. It's kind of strange, but anyway, there's kind of an analogy where we think about a distillation. If you're sitting at the lab bench and you're distilling, you can separate compounds in the distillation, distill some compounds over. And so there's kind of the concept that one theoretical plate is equal to doing one distillation. Two theoretical plates mean you take that distillate and you distill it again, you get a little better separation. And you keep on with the idea. adding on distillations and improving. So we want our theoretical plates to be large. The more theoretical plates, the better job we're going to do in separation. So we want to be selective. We want to choose the right column. We want to have a capacity term there, like say, I'm going to pass that over for the time being. And we have a large N, a large number of plates. So what do we work with? How do we deal with these things in terms of changing parameters? Well, okay, here's the slide where I defined that. Okay, here, expressing column performance efficiency. And so I'm going to use that plates idea. And we typically say how many distillations per meter of column. My columns in gas chromatography are typically 30 meters long. And for efficiency, we break it down and say, what do we get for each meter? That way, if you've got a longer column, shorter column, we can adjust that total number. HETP, that's a height equivalent per theoretical plate. Basically, that says, how long of a column do I need, or how much of a column do I need to actually get this one distillation? Do I need that much column to get one distillation, or that much column? So we want efficiency to be high. We want large number of plates. HETP, we want to be small. I want to have smallest length of column to get a distillation. So I can have many, many, many distillations, right? Okay. So let's take a look at this and give some idea here. So here's my column efficiency, my plates per meter. In gas chromatography, we can look at a range of someplace around 1,200 plates, look at the y-axis, up to perhaps 9,000 plates. And so what do I have as the x-axis down there? The column diameter. How big is my column? My columns can be as small as 0.1 millimeters in diameter, tiny, tiny columns, or they can be up to 0.75 millimeters, which is immense as far as we're concerned. So we can be anywhere in there. What do we want if we want to have efficiency? Small columns, small bore columns. What do we want if efficiency isn't so important? Then we probably go with a larger column. Larger column, we can put more material on, larger samples, maybe see something. So the idea, we normally will go for a very small column. For us, and you look how fast that number goes up as you go small. It goes up very, very quickly. We typically work in about 0.2 millimeters. So that'll be the inside diameter of our analytical column in the gas chromatograph, probably that you use. It might be 0.25 that you use in class, one of the two. And that's operating in a really good efficiency range. You might say, why don't we do 0.1? Well, at some point you don't have much phase in there. You can't put much sample on there because it's so darn small. So that's kind of too small to work with, the 0.1. Very efficient, but too small to put sample in and get any capacity out of it. And so we typically go with about 0.2 to 0.25 as internal diameter. Now this one is our height equivalent per theoretical plate, and I don't know why I don't have them on the same units. In this case, remember, we want HETP to be small. The smaller, the better. So the previous one, we want them large. Here we want them small. What gives us a small HETP, high efficiency? Well, that mobile phase is important to us. It's very important to us. It's interesting, if you look at what gives you the lowest number, absolute lowest number, it's nitrogen, right? That bottom down in nitrogen is really you would say, the best column in terms of efficiency. And then we've got hydrogen and helium that kind of come in about the same. The problem with nitrogen is, look what happens when you start going a little faster flow rates. Your x-axis here, average linear velocity, that's basically meters per second that gas is flowing. I'm sorry, centimeters per second that gas is flowing. And so if we're going to do something like nitrogen, I have to stay around 10 centimeters per second. And I've got a 30-meter column. How long does it take that gas to get out? How long does it take for my column to elute? It takes forever. That gas is moving so slowly. So wonderful efficiency, but it takes me forever. I get fired, I lose my job because I don't give any results. I'm still waiting for my sample to come out. So what do? We compromise, right? And then we start going higher and higher flow rates. So if we get up to 30, 40, 50 centimeters per second, that's moving right along. And at that point, we've lost a little bit of separating power. It's not as good as nitrogen down there at 10, whatever it is. So it's kind of cost us a little bit, but not a great deal. And so I can look at hydrogen or helium, and I can have really that gas going through a column, mobile phase very quickly. I get quick results. And if you start looking and say, I really want to push this sucker, we look out 60, 70, 80, 90 centimeters per second, hydrogen shines. And hydrogen then is a good, really good choice. So most people use helium. Why? It's inert, it's historical. We have nothing but hydrogen throughout our laboratory for all of our equipment. It's simply more efficient at high speed. It gets us data more quickly. So column, we think about diameters, we think about flow rates. There's another parameter we have to think of when we're trying to optimize this separation or get good separations. And one, as I said, there's a coating inside that column, right? Okay, how thick should that coating be? Should it be a really thin coating or should it be a thicker coating? And that's a decision you have to make as a user. You have to decide on the length of the column, you have to decide on the diameter of the column, type of coating inside the column, and of course now the thickness of that coating inside. And your efficiency is influenced, as is capacity, by the thickness of that film. Thick phases, you've got a thicker coating, they're not as efficient. So we get poorer separations. They handle bigger samples. So is it important to have big samples? Or is it really important whether we're getting separation of that sample? And so poor separation for thick phase, better separation for thin phase. We typically go for a thin phase. So we may have a coating of a micron in terms of thickness. Column length, the longer the column, the better the separation. If you've done any chromatography, I don't care if it's a glass column sitting on a bench, or if it's a very fine column like we're working with and to the side of an instrument. The longer the column, typically, the better the separation. But that comes at a cost. If I have a 30-meter column and it takes me 10 minutes to do my analysis, I could double that and get better separation, but now it took me 20 minutes. Time is money. When you think about it that way. And so you have to think about is what important is time versus separating ability. Also, what happens is your improved separation is only the square root of 2, 1.414 times better. If I double my length, I get 1.414 times better separation, but it costs me twice as long. Do I really want to pay twice as much to get 1.4 times better separation? So again, we keep our columns shorter if we can. The shorter the column, the happier we are, the faster we get data. And so when you look at kind of making these judgments, you kind of get this type of a pyramid in a sense. Do I really want to put a lot of material in my column? Do I want to maybe trap something, collect something? Well, then I choose a certain set of columns, lengths, diameter, phase thickness, and so on. But keep in mind, if I'm out there towards capacity, I'm losing speed, sensitivity, and resolution. So what's most important to me? Conditions that give me retention, it's at the cost of speed, sensitivity, and so on. You don't get everything. It's like life in general. Make your, pick your choice here because you're not going to get it all. So what's important to you? If you have a tough separation, it's at this cost of speed, sensitivity, and capacity. So there's a lot of thought that has to go into choosing that column and selecting the right column. And again, how do you make that kind of choice? usually by looking at literature, what have other people used. But again, I guess I'd always caution you. I always assume that somebody else did something exactly the best that can be done. So you look at what other people did, but then you also sit down and think about it. Is that the right choice? Is that the right way to go? It's a starting point. But don't simply use it blindly and say, well, this is the only way to do it. So we're going to make troubleshooters out of you too. So, okay, the gas chromatograph generally works pretty reliable. It's pretty reliable equipment, but things do go wrong. And so I'm going to hit up what are the major things, the most common things that go wrong. And in terms of what goes wrong, 80% of the time it's plumbing. That may sound funny, but what do you have? You've got gases under pressure. We have all kinds of connections. We have all kinds of septa, ways in, ways out. And sometimes things aren't looked at after well enough, and that carrier gas doesn't go where you thought it would, or not all of it goes where you thought it would or should. And so 80% of the time, it's a plumbing problem. You start looking, okay, where's my mobile phase coming in? Am I delivering it? Am I delivering what I think? Is it leaking here, leaking there? What's happening? So that's 80% of the time, just a plumbing problem. A good plumber could come in and fix your gas chromatograph 80% of the time. Well, I don't think I'd call one of the local plumbers for this, but they would have the ability to find the problem. 10% of the trouble is due to operator error. Okay, we screw up 10% of the time. 10% is truly hardware problem. We've got gas chromatographs upstairs that I would guess are 35 years old. They're in that ballpark, and they still operate. That hardware still works. The software still works. The valves still work. Failure of the hardware is really rare. 10%, I think, is being rather unkind in that sense. Most of the time, I would give it more credit to the operator, how's that? And a little about the same to the plumbing issue. And so that 80%, the idea of plumbing problem, gas is not going the right direction. The best way to do that is to run internal standards, internal standards maybe, but let's say we run control samples. Anytime you start off the gas chromatograph, I just love to see a student go ahead. Here's a model mixture. That resembles my sample. I'm gonna make an injection of that and say, do I see all the peaks I thought I should? Do I see all my compounds? Are they about the same size they should be? Do they look nice and sharp? Okay, so the idea, having an instrument quality control sample. And of course, you get into methods quality control, or methods quality control, yeah, quality control sample. That's really different than an instrument. So the instrument, you've got a known mixture, you see the instrument performing. In terms of a sample, that goes all the way back to maybe when you start the sample, start your extractions, isolation, carry it all the way through the process. And I do make the comment on the bottom, these are instruments. They may look like plumbing, but you do have to be sensitive to them and not abuse them. They are delicate precision instruments. The other kind of 20% method quality control samples, hardware failures, like I say, the idea that it just generally doesn't happen. If you do a maintenance, and there is maintenance for these, and oftentimes, particularly in the university environment, that preventive maintenance isn't always done. If you look at a new instrument today and you want to get a nice service contract, so they will come in and do the service for you. They'll come in and tune up your instrument every now and then. What is it? Is it 10% of the cost? Did you it of the cost of the initial instrument each year? It goes up a lot, and if you think about it, you buy a $100,000 instrument, you're paying $10,000 a year to have them come in and keep it up for you, or $200,000, you're paying $20,000 a year. universities typically don't have that kind of money. Maybe if you're in some analytical service, you could charge people. It happens. But again, in academic life, that's tougher. We have to do that ourselves normally. And it's something we must do ourselves and do it well. We typically will be trained in that, or at least we have manuals and can tell us how to do maintenance, and we have to do it. We absolutely have to do that. This just shows where our 80%, our plumbing problems occur. How's that? And so up at the top, where we put our sample in, we inject through that septum. That's where we put our syringe. We pierce a hole in that septum into the high pressure gas flow line. What's a nice place to leak? You know, poking too many holes through it. Pretty quick, there's a big hole. Pretty quick, there's gas flow out the top of the septum instead of down through where it should be. So first thing you look at is the septum that's on top. If you look at the next place, there is a seal. That's glass. See the septum and right under that seal? There is a rubber seal to a glass vessel inside of that injection port. And so sealing glass to metal, we use a nice rubber donut type of seal. I've seen them actually turn to dust that people have not changed them. What a great place to leak. People just don't look after it. So make sure the seals at the top of this injection port are replaced. Now maybe once a month, maybe once every 2 weeks, but somewhere in that range. Our third one's down here at the bottom. This is all under pressure. We're going to attach this little capillary column here down to the bottom of that injection port. Again, that's another seal. That's a graphite seal. But again, is it tightened too much? Is it tightened the right amount? When's it been changed recently? We can have problems too. Over on the right-hand side, the splitless valve, that's supposed to be operating. It's supposed to allow you to inject something into your sample, dump everything into the column, and then open. Sometimes it doesn't open if it's not maintained. Well, that just screwed up your results all over. And so that purge line also can become plugged. So the valve, the split on the end. And so those are the main areas you look for problems and you do maintenance on. I should also mention, just right down on the bottom of this one, where we see the column, this nice circular column is attaching there, there's a gold disc. I shouldn't tell you about the gold there. Now you go mining, okay. It's a gold disc on the very bottom of that. So if you look at the tube coming down the center of the ejection port, there's a gold disc down there. And that is what makes the seal between the glass and the metal. And again, if that isn't cleaned, if that isn't replaced about every 3 months, 6 months, it again will build up material that's a catalyst and breaks down your column. So again, maintenance, absolutely critical. So this is some GC applications. So talking a little bit about how we apply different samples. If you think about it, most of the time, you're going to do some type of extraction, some kind of isolation of your sample, treatment of your sample. In some cases, Chelsea, one of Bram's students, is looking at oxidation of foods. She can go ahead and actually put that food into a closed vessel, let it sit a few minutes, and the oxidation, the hexanal, compounds that are characteristic of oxidation, will come into the headspace. So you can actually take a GC, sample the air above the headspace and inject it. But most of the time, you're having to do some more simple, and I shouldn't say simple, some more complex extraction and isolations. And so you always have to think about how you're preparing your sample. Let's look at a couple of examples of that. There's different ways to do these separations. I think Cindy is probably going to show some of these. Is she going to show SPME? And do you remember?
I think no. I think we just do whatever we need for the fatty acid.
For the fatty acid analysis, okay. But there's some pretty neat methods of doing concentration. I won't go into any detail, but the SPME twister, the SPME is a needle that's coated with an adsorbent material. And you can put that adsorbent material into the air above a sample. Put the sample in a closed vessel, put that needle in there as an adsorbent, you allow it to sit for 10 minutes, 15 minutes, it's sucking in any volatiles onto that fiber, pull the fiber out, put it into a gas chromatograph. The heat, the injection port, releases the compounds. We've got other ways where we bubble nitrogen through a sample, and then that nitrogen will pick up some aroma, something from your sample. That goes through an adsorbent, and so we keep on purging the sample with gas. That gas goes through an adsorbent, loads up an adsorbent, that we eventually heat and desorb. There's all kinds of different methodologies, and each of them has their own pluses and minuses. This is what we call the SPME, and this is what I said about, if you look at the lower left-hand corner, very fine needle down there. So we can actually pierce a septum, get it into a sample one way or another, and that fiber will absorb the volatile compounds. This is our twister. It's a little glass bar, smaller than most of your stir bars, that has a coating on it. It's a PDMS coating. We can put that into a sample, a stir bar. We can have a liquid, we could have juice, we could have milk, we could have whatever. Drop the stir bar into the milk and sit that stir for a while. It'll absorb compounds onto it. Pull it out, rinse it off, drop it into 250-degree injection port, and poof, we've got, again, our sample isolated. So there's all kinds of different ways. And again, that's a whole nother 2 lectures, how's that, on different ways to get a sample into an instrument. We're only going to touch on a couple here. This one is related to flavor. We actually can make some really nice coconut flavor by fermentation. The problem is the flavor compound has chiral activity. One chiral form of that flavor compound doesn't have any taste or smell at all. The other chiral form does. And so we need to distinguish between 2 chiral isomers. That's an exceedingly difficult challenge because the chiral compound is nearly the same, all physical parameters, the same volatility, you name it. And so it is a real challenge to look at. The compound is delta decalactone. That's a beautiful coconut component. And so how do we go about measuring this component? We do it by gas chromatography. Are we getting the right isomers being formed? Fairly simple, culture medium extracted with diethyl ether. Our aroma compound is soluble in ether. So if we've got a water, where we're fermenting this product, you can take some of your fermentation broth, add a ether to it, shake it up, collect the ether, go through a fractionations, because that ether will pick up a lot of things. So we put over a small column and that'll fractionate it. We pick out the right fraction, fraction 4, and then we can go into a gas chromatograph. And we have a chiral column. So this column is a very unique column that's great at separating based on structure, not volatility, not polarity, but structure. And so we can go ahead and get a chromatogram that looks something like this. There's 3 different lactones here. There's an unsaturated and saturated, but it separates the R and the S each time. We have to make sure, like I say, it's the right chiral isomer. And that's, like I say, a really tough separation to do, but it lends itself very nicely by this particular methodology. So chiral isomers. This one I like because it's simple. I like simple things, basically. The simpler it is, the happier I am with it. So, okay, diphenylamine is used to treat apples prior to storage to control apple scab. Apple scab is a fungus, I believe. And so apples are dipped in a solution, 1 gram per kilogram. That solution is diphenylamine. Diphenylamine inhibits this fungus. And so we're really concerned, is there a residue of this diphenylamine for the consumer when it gets to the consumer? And so you need some way of monitoring the surface of that apple and say, is it does it meet requirements or not? I love this kind of isolation. Simply wash the surface of the apple with the solvent and concentrate for analysis. We use a 3-minute soak in hexane. That's how we wash the surface. Concentration, so we just take that solvent, put a little stream of nitrogen on to evaporate the solvent. The solvent's very volatile. Your diphenylamine isn't very volatile, so okay, we can reduce the solvent and then take and inject that. This is what you get if you wash an apple, what's on the surface. Now, each of those peaks are a different compound. So that's your gas chromatograph that you get off it. It isn't like, oh, we see diphenylamine, we see everything that's come in contact with that apple, anything the apple might have generated in the process as well. So this is a place where, again, mass spectrometry is absolutely beautiful, something you love, because the mass spectrometer can go through each of these peaks and say, hey, this is the particular peak that corresponds to the diphenylamine. So this is the mass spectrum. Again, we'll talk about mass spectrometry. It takes a molecule, blows it into bits, and then you take those bits and you try to match up some compound. What compound blows into those fragments or bits? So these are what happens to the diphenylamine, breaks into fragments of these different sizes. Then you can have the mass spectrometer look for those fragments. So your gas chromatograph is running along, one compound, 2, 3, 4, 5. When the right compound comes by, those that give those fragments, you know that's your compound. And that's basically what's shown here. The top tracing is of a sample that's been spiked with the diphenylamine. So over in your far right, it's DPA. Okay, I spiked my sample, that peak got bigger. The apple extract, you see DPA is a small peak. After I spike it, it's a big peak. Okay, that's the right compound. Now he's got to run a blank. And in this case, there's absolutely nothing in the blank because I keyed it, the mass spectrometer, to only look for compounds that fit the fragments, the bits and pieces of the diphenylamine. So it's a fascinating tool, extremely powerful tool. It comes right down to it. You're going to be using this to do fatty acid analysis, this technique for fatty analysis. We probably won't get through that, but that's okay because you'll learn it when you do it. How's that? What you're going to find is you're going to end up getting a chromatogram. Either you or Cindy or one of the TAs will run known fatty acids, and that's what's shown here. We've got butyric, caproic, caprylic, all of our fatty acids that we find in foods. The butyric acid dilutes is the first peak, second peak's C6, caproic acid, and so on down the line. And those compounds are going to come off at exactly those same places in your sample. So you've got a standard. I know at 1.769 minutes, butyric acid's going to come out. When you run your sample, if you don't have a peak at that exact time, it isn't there. If you get a peak at that time, it is butyric acid. So what you're going to have is an opportunity to run a standard and based on time, elution time. And that is reproducible, typically to 100th of a minute. Every run will be very consistent. So you're going to do comparisons back and forth between the standards and your sample. In the end, you are going to get a profile like this, and that profile will give you, or the report will actually give you areas under the peaks. And that's what you're going to be comparing to say how much is present. So the machine's measuring the area under each of the peaks. And so that area is proportional to the amount of compound. So Cindy, whoever will go through that with you, it works really quite well, obviously. It is the way it's done. Are we okay? Yeah. Okay, good. If you have any questions about any of this, stop and see me or set up a Zoom meeting, whatever. It's a fun technique.
HPLC is funner.
Okay.
HPLC is funner.
HPLC is funner. Did you hear me say that? That's not true. We always have our battles about this.
All right. Good. Stop sharing.